Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss the concept of effect of variation of velocity on friction in the suction and delivery pipes. So last class we have seen the variation of velocity and acceleration in the suction and delivery pipes due to the acceleration of the piston in the reciprocating pump. So here we'll see what is the variation of velocity on friction in the suction and delivery pipes. So we know that when the fluid is flowing through a pipe, there is some losses due to the friction, and that is called measure loss. So if you remember that the working principle of reciprocating pump, how it is working. So we have a delivery pipe, like suppose the delivery pipe is here, and this one we can draw like the cylinder and piston which is present here, and this is suppose cylinder piston, and this pipe is suction pipe, and the suction pipe is connected to the reservoir of the fluid, or you can say the this is sump. This one we can call as a sump, and in this we have the piston is there. This is the piston, and the piston is connected to the crank like through this piston rod, and this piston rod is connected to the crank, connecting rod. Then connecting rod is connected to the crank, so the crank will be here. Suppose now this crank will be rotated within direction, in this direction suppose. So, and we have seen up to this, like what we have discussed. So why I've shown you here, like this is the working principle of reciprocating pump, and then this, like the water will be come here, and here we have the suction valve, and delivery valve will be here. Let me highlight this. This is our suction pipe, and this is our delivery pipe, and this is our delivery valve, and this is our suction valve. And here we have, this is the cylinder, and in the cylinder it contains of, this is the piston, part is piston. Okay, and this is the piston rod, this piston rod, and this is the connecting rod. So these are the components in the reciprocating pump. This connecting rod, and this is our crank. So the crank is rotating here with an angle of, here angle of theta, and suppose this is A point, this is O point, this is B, and this one we can give C, this is our D point. So the crank will be rotated in this direction like this. On revolution it will be completed. So it will move, the piston will be moved forward and backward directions. Okay, so what already we have discussed these things, just I'm giving brief idea about that, because we need to take the velocity value from this equation. So let first, due to the friction, we know that due to the friction, we have this one already we have studied in the fluid mechanics. Due to friction, in the loss of energy, we have seen due to the friction, which will come under the measure loss, measure losses of energy. So measure loss, we have seen the equation, that is Darcy-Weber's equation, and there we have found that HF equal to 4F LV square by 2TG. This is the head loss equation we got during the friction or during the pipe losses. So here also is the same thing, the effect of variation of velocity. Okay, the velocity variation, or what is the effect of this velocity variation on friction in the suction as well as delivery pipe, because we know, see, this is the pipe is there, so water will be flows through the pipe. So due to the friction of this in the surface of the pipe, there is some losses will be there. So how this velocity is varying with respect to the friction, so that we'll see here. Okay, so this is the head loss, you can say loss of head due to the friction in the pipe. Normal, I've taken for both, for suction and for delivery also, same equation will be used. Now, so here if you see this 4F LV square, so velocity, this velocity we need to consider from this reciprocating pump. That's why I have shown you this diagram. So velocity, we know that what is the velocity is there. So velocity equation, we know that how much distance traveled with respect to time. So dx by dt we can write. So here dx is nothing but how much distance traveled, in the sense, if I consider here, suppose this is the, let me change this color so that you can see this one. Now see, this is our OB point. Okay, and this crank is rotated up to here, and which is an angle of theta. If I draw the line here, then we can get a triangle here. So because that much distance traveled, okay, this is E point, this is F point, and this is our R, radius is R. So now distance traveled from A to F point, because the distance traveled by the piston. Okay, that's why that is the velocity. So how much distance traveled? Suppose the piston reached here. Meanwhile, this much distance reached. This is starting point. After that, some distance I have kept here. And when this is at this point, suppose the piston reached here. So how much distance is covered? That is x. So similarly, this x also here. Okay. Now we need to find out this distance traveled. So the distance traveled here actually, I can write the distance traveled x, okay, by the piston. You can write this is to AF we need to calculate. So to calculate the AF, I can write AO minus FO. So AO value is nothing but the radius of the crank. That is x. Sorry, you can write this is R. This is R. And what about this FO value? FO value, this is theta is there. So you can write R is cos theta. So I can write this is R cos theta. Okay, and theta value actually, the theta is nothing but that is the angle turned by the crank, and in the radius, that is in with respect to time. So theta is nothing but how much crank is rotated. So this crank is rotated with an angular velocity of omega. So with respect to time, so we can write omega into t, theta. Okay, so you can put the value of omega t here, and we'll find out, we can get it here, like x equal to R minus R. This is cos omega t. These things already I have told you in the last lecture. So just I'll show you that v value how we have taken. And here, so v equal to, we can write this is derivative of this R minus R omega cos omega t with respect to dt is there. And finally, I'll get the value that I'll write here, that is omega R, and this is sine omega t. Okay, this is the v value. Okay, this is the velocity value. Now, and the velocity here actually, this is velocity of the piston. Okay, here the velocity is different. So the velocity of the like the fluid, the velocity of the fluid in the pipe, that we need to consider. So this is only velocity of the piston, but velocity of the pipe we need to consider, we need to calculate from the continuity equation. That also I told you, that is AV. A in the sense area of the pipe, velocity of the pipe, velocity of fluid in the pipe, and area of the cylinder. Okay, let me take this one, a small AV, this is capital AV. So this is area of the cylinder, and this is velocity of water in the cylinder. Okay, similarly, velocity of water in the pipe, and this is velocity of water in the pipe, and this is area of the pipe. Okay, so now I will consider this is small v. The small v equal to, I can write capital A by small a into capital B. So here I can write the value a by a and omega r. This is sine omega t. This is the v value. This is the v value is what? This is the velocity of water in the pipe. So that is the velocity value. So this value I supposed to take from this concept. That's why I've written this. Now I'll put this value of velocity in this equation. Okay, so what I can get here? So I can write HF equal to, I can write HF equal to 4FL, and here 2 dg is there, and on behalf of v value I'll put this equation. So in this equation I can keep it. So that is capital A by small a, and this is omega r, and this is sine omega t. Okay, omega t plus we can write theta also here, that is square. So you give this equation number, this is suppose 1, this is equation number 2 we can give, and this one we can give equation number 3. Okay, now so let's make it in terms of theta. So theta will be, if I write in terms of theta, then I can write 4FL by 2 dg, and this one also you can write capital A by small a, and this is omega r, this is sine theta, this bracket square. Now if you see the head loss with respect to theta is what? This is the crank angle. So how much movement will be there? Okay, then based on that, crank will be moved, so it will be like it will be rotated here. So the head loss, the variation of this head loss, okay, with respect to this theta will be a parabolic. Okay, so the loss of head due to friction, what we have discussed in the suction, see, the loss of head will come in the suction pipe as well as in the delivery pipe. Okay, so that can be calculated from this equation, from this equation. Now this is the main equation. Now suppose I want to write the suction head, what is the head loss in the suction and in the delivery pipe. So that we can also write based on the same formula. Just you can put it HFS. So S we can give for suction. So we can write this is 4FLS. So L is the length in the suction pipe, and this is 2DS. So suction pipe diameter, and this is 2DSG. And here we can write A area, and this is AS small s omega r. This is sine theta bracket complete square. This is our suction. Similarly, for the delivery, we can write the same thing. HFD equal to, we can write 4F LD divided by, here also the same thing we can write 2DDG. Okay, and bracket start capital A by small ad, and here also omega r, and this is sine theta bracket square, and this is equation number 5. So the head loss, the loss of head due to friction, the loss of, this is loss of head, this is due to friction. Okay, and here these two equation we got same thing, but this is for suction pipe, this one we got for suction pipe, and this is for delivery pipe. Okay, these two things we got. Now, so the loss of, if the loss of head due to friction, that will vary with the theta, correct? So here if the theta value will be changed, suppose when theta equal to 0 degree, theta equal to 0 degree in the sense the crank is at the starting point. So in that condition, our sine theta value will be what? So sine theta will be here, that is 0. Okay, the sine 0 equal to 0. So if that is the value, then what will get the HF value? HF value will get here, this part will be 0. Okay, so this part will be 0 means the total part will be here, HF equal to 0. That means it is in the starting position, there is no movement is there, that's why there is no loss. Okay, that is the meaning. The second condition, if you say, that is when theta equal to 90 degree, a partial movement of the piston is taken. So sine 90 equal to what? Sine 90 equal to, that is 1. So here we'll get the value. What is the thing is there? So same thing will get, like HD or HF equal to, we can write this is 4FL divided by 2DG, and this is A by A, and this is, we can write omega r bracket square. Okay, and the third one, if I say when theta equal to 180 degree, so theta equal to 180 degree means sine 180, sine 180 equal to, we know that is 0. Again we'll get HF equal to 0. That means when this crank will be reached at this point, that means the piston will be reached at this end of this. So that time there is no movement is there. That means no movement of fluid in the pipe. So at that point also we'll get the loss of head is 0. As simple as that. So I told you already previously, at this point there is the velocity of this piston is 0, and at the middle of this point we'll get maximum. That's what we got here also. So from this concept we can write the HF maximum. So we can write the maximum loss of head. So that we can write this equation, the same equation, just we can write, and we'll put the value 4FL by 2DG, and here we can write in the bracket, this is capital A by small a into omega r whole bracket square. That is what we got for the when the angle is 90 degree. Okay, this is the final answer, the final derivation or final answer we can say. Now in meanwhile, I hope you understand it is very simple. When this piston is at this permin, that means the there is no movement in the pump. Okay, it is in the starting condition, the velocity of the pump is 0 or piston is 0. So when it, at this point v equal to 0, and when the piston reach at this end of this, that also velocity will be 0. Again it will start here, forward and backward directions. It will continuously move forward direction, backward direction. So at this point 0 degree will have the head loss 0. At this end of this point also will have the head loss 0. Only at the when it will reach in the peak point, that means the middle point, then it will have the maximum head loss. That's what we also discussed in the last lecture. So here some terms I have, this is F. This already we have discussed previously, that's why I have not informed you that F equal to coefficient of friction. Okay, this is coefficient of friction, that already we have discussed. This is coefficient of friction, and here length L is the length of the pipe. The length of the pipe we can consider for both suction and delivery also, delivery pipe and suction pipe. Length of the pipe, along with that V is the velocity of pipe. Already I told you, V velocity of the pipe, then D is the diameter of pipe. So diameter of pipe also can be varied. That this is for the suction diameter, this is for the delivery diameter. Similarly, area of the suction, area of the delivery, and length of the suction, length of the delivery. So I hope you understand this effect of variation of velocity on friction in the suction and delivery pipes. So this is simple concept, but sometimes the questions can be asked in the exam, it is in the syllabus. I hope you understand. If you are having any doubt and query regarding this, you can give a comment on that. Thank you.